Welcome to WhiteBox Learning Flight 2.0. As always, students will log in here on the application login page with the same ID they would use for our other STEM applications. But first, please make sure you have added Flight 2.0 as an activity in whatever classrooms you choose. Please review the Teacher Control Center demonstration video for instructions. Flight 2.0 is a turnkey applied STEM unit created to teach the principles of aeronautics in an engaging and accessible manner. Purely cloud-based, your students will be immersed in a modern, exciting, STEM-intensive, virtual, and physical glider design unit. The learning system contains fully integrated, standards-based math, science, and engineering content, 3D design and analysis tools, a game-like simulation, and all the custom plans and materials necessary to take our virtual learnings into the physical realm by building a real model of our optimized design. Flight 2.0, like all of our STEM applications, is unique due to its unrelenting focus on all 4 letters of STEM, woven together in the same place at the same time. The user interface is the same for all WhiteBox STEM applications. It contains sections for research, engineering, a game-like simulation, in this case the air show, outputs, and build and test. Let's start with research. Students begin with background and design specifications. You will find that each section builds on the next. The design specifications, or rules of the challenge, are established by you, the teacher, in the Teacher Control Center and can be modified effortlessly to initiate new challenges and new learning. Next, in the Knowledge at Work section, students begin with an overview of the science of flight. Remaining sections explore the details of weight, lift, drag, roll, pitch, and yaw, and how all of this comes together to predict how well their glider will fly. Numerous quizzes and worksheets are woven throughout the content and provide immediate feedback to the student. And the tutorials are designed to explicitly reinforce this content by showing your students how to turn theory into action. For example, in the lift-drag analysis tutorial, the equation for lift, which was previously introduced in the research materials and reinforced with quizzes and worksheets, is displayed again. But now, students are taken through a step-by-step process of how they can use the application to study each variable in the lift equation, and how changing these variables affect overall lift. Furthermore, and this is very important, this analysis is performed entirely within the context of the student's own design. They create and analyze their own designs. In your Teacher Control Center, you will find a pacing guide that offers implementation suggestions for how to move your students through the Flight 2.0 STEM application. All the while, as your students are working through the application, we are reporting for you in real-time, actionable metrics, including content reviewed, student time on task, and quiz scores. Then, we report the link between the students' content knowledge and their design solutions. In other words, between their effort and their performance. One very important purpose of these measures is to help teachers recognize when to intervene in order to improve the learning process. So the WhiteBox Learning Framework provides a mechanism for true formative assessment, real-time, actionable feedback for students and teachers. The engineering section provides a complete suite of modeling tools to design and analyze my glider. Please remind your students that placed throughout the research materials are numerous tutorials that will help them become comfortable with the modeling tools in the engineering section. These tools are easy to use because they are built for a specific educational purpose, to reinforce the STEM content associated with glider design. Within minutes, students can modify the shape and position of their fuselage, wing, and the horizontal and vertical stabilizers to create very different designs. This simplified, streamlined use of intelligent CAD technology empowers students to get on with what we call the good stuff. That is, the underlying science, technology, engineering, and math that students can immediately apply, putting theory into practice, and thereby further developing their critical thinking skills. For example, here I am using the sketching tool to modify the shape of my wing. Once I click Apply, I can immediately see the change in my 3D model. But what are the implications of these changes? The answer to this question leads us to the good stuff, where we want our students to be. The analysis tools immediately reveal that this change in the shape of my wing will affect weight, lift, drag, center of gravity, and the location of the neutral point. So this simple geometric change will affect 3 of the 4 forces of flight and stability. The research materials prepare your students to digest and act on this new information. Flight 2.0 is calibrated to maximize STEM learning. Students are provided all the information and tools necessary to make theory actionable, but not so much that the application does their job for them. In other words, students must tap into their own higher-order thinking skills to make informed design decisions. And, since this is real, solid modeling, there are no preset outcomes. Your students are creating and analyzing their own unique gliders. Accordingly, endless outcomes are available for your students to explore. Next, I can select File, and if I am ready to test this design in the air show, then I give it a name and can immediately find it categorized as a staged design. Then, I can compete against any other student who has entered a design. It is worth pointing out here that with a multi-school or district license, teachers are connected as friends, meaning if the teachers sanction it, then their students can compete against all students across their entire district. The air show includes 2 gliders competing for longest duration. The scene itself, dynamic camera views, sound, and a leaderboard all add to the excitement. Though to the students this may look and feel like a game, it is actually an extraordinarily powerful analysis tool. Once the air show is complete, students are presented with detailed results about both designs. There is a lot of information here, but we purposefully do not tell students specifically how to improve their designs. That is their job, the student's job, to interpret these results along with everything that's come before it and to develop and act upon their own theories. Students can literally research, design, analyze, and simulate hundreds of times, learning more STEM with each informed iteration. In this engineering challenge, the path to the leaderboard is through effective critical thinking. This method of building and testing virtual models before actually building physical models has strong roots in industry. But where the objective in industry is to maximize productivity, our objective here is to maximize learning. The fully integrated nature of this learning system, the ease with which students can move between research, modeling, and analysis, and certainly the more exciting elements of a game-like simulation, all compel students to design and test numerous designs before actually building a physical model of their optimized design. Now, connecting the virtual to the physical. The outputs and build and test sections include a variety of reports, print templates, and instructions for building a physical model of their optimized design. While Flight 2.0 can be used as a completely standalone virtual learning system, we believe there is great value in building and testing a real model. Accordingly, we can assist you in making provisions for the actual kits your students will use to build their physical models. Please see our website for our kit offerings. So, how do the four forces of flight work with and against each other to produce flight? How does wing design and placement affect the performance of my glider? What is the relative importance of weight, lift, and drag? What design changes most affect stability? What is the center of gravity? What is the neutral point? And why does the relationship between them matter? The WhiteBox STEM Learning Framework empowers students to ask and answer these and many other questions for themselves. This is higher order thinking, an essential key to an effective STEM learning process and beyond. This concludes our Flight 2.0 demonstration. Thank you, and as always, if you have any questions or need any assistance, please don't hesitate to contact us.